Yeah, thank you. Alright, so good afternoon everyone. How are you doing? Doing alright? Yeah? Okay. At lunch? Yeah? Okay. Alright, so let's do a big recap. Right, so what we have been doing thus far is we have discussed what perfect matchings are. Right, so it's a set of edges, so that if you look at any vertex, let's say the pink colored edges, if I look at any vertex, I will see exactly one pink edge around it. And if it is at most one, then that's a matching. Right? And what we did is we wrote down an ILP for perfect matches, integer linear program. The point is, if you look at this ILP, and of course in the interpretation, which we discussed last time, the way we are interpreting is an interpretation of variables. If I give you any solution to this system, what's the system? At each vertex the sum is equal to 1, each of these is non-negative, and each of them is an integer. That's exactly what a perfect matching is. If you interpret all the x's that are equal to 1 as edges in your matching, and x's that are equal to 0 as edges not in your matching, then what you will get is exactly a perfect matching. Right? So the interpretation is xe equal to 1, we interpret that as E belonging to the set M, and xe being equal to 0, we interpret that as E not belonging to the set M, where given an x, we get an n as follows. Right? The x is the solution to the system, and what we have just defined here is a perfect matching. And if you, instead of equality, if you put a less than equal to, what you will get is just matchings. Right? If I replace this by less than equal to, then what I have is all matchings, not necessarily perfect. Yeah? So that's that. And what we are more interested in this course, combinatorial optimization. Here is our first combinatorial optimization problem. So you are given a graph and you are given costs on the edges. So we just took your graph, for example, and I will put the cost in another color. So let's say 7, 1, minus 3, minus 2, 4, 0, 9, 8, 11. No, I don't like 11, I like 3. Second. Okay. Okay. So if these are the costs of the edges, then what we may be interested in is finding a perfect matching in this graph that has minimum cost amongst all perfect matchings. And the cost of any set of edges is simply defined as the sum of the cost of all the edges. That's one way to define cost of a set based on the cost of the elements as yes or no. Right? So that's our first optimization problem, and we will see how to solve this problem by the end of this course. It's a long way away, but that's okay. Right. And if you have these cost functions, what you can write down now is an integer linear program for the mean cost perfect matching problem. So if that's my optimization problem, here's my integer linear program. I'm trying to minimize this function subject to these constraints. So this is called the objective function. Whatever you're trying to minimize or maximize, and these are called your constraints. Right? So within all solutions to the system, we are trying to find one that has minimum cost. Right? Good. And one thing you could do in life is you can try to make your life more difficult. Right? And one way to do that is to remove some constraints and look at a larger set and then try to find a needle in the larger haystack as opposed to the smaller haystack. So we will do that, and that gives us what is called relaxation, also an LP relaxation, but all relaxation in this course will be LP relaxations. We'll get an LP relaxation of this problem, which is basically the same thing. You simply drop not the course, but the last step. Right? So if you drop the integrality constraints, these are called the integrality constraints, as I wrote down somewhere. Right? So these are the integrality constraints, and if you drop them, then what you get is a linear program. So now we are looking at all solutions to this system instead of just integer solutions. And within this system, we might want to optimize. Of course, that changes the problem. If the minimum is attained by a solution that is not integral, and if you find that one, then that's actually meaningless. We still want to solve the original problem, which is the minimum plus perfect matching problem. So what would be nice is if in this system, after dropping the integrality constraints, somehow the optimal is still attained by an integral point. That would be nice. And if you can find such a point, then we would have solved the original problem. Right? But in general, there is no guarantee for this to happen. Yeah? Anyways, we'll get back to these points. But now I want to go into a more formal discussion of what is a linear program, because we haven't really defined it. So let's define this. Yeah? So this is just an example. Let's talk about linear programs, or sometimes people like to use linear programming. And contrary to what the name suggests, it has nothing to do with programming as we typically think of it. It has nothing to do with programming or coding. So what's a linear program? Well, before we define a linear program, we'll define a linear function. I'm sure most of you know it, just so that we are on the same page. Let's define. Let's start with basics. What is a linear function? So if I have some variables x1 up to xk, then the linear function is alpha 1 times x1 plus alpha 2 times x2. That is the thing I use. K, I also think that's, I just give an example to think from share. Who needs K? Okay, so if my variables are x1, x2, x3, and this is the linear function where all the alphas are real numbers. Yeah, so that's what the linear function is. And sometimes you also want to add an extra constant to a linear function. Those are called affine functions. It's just a translation of a linear function. An affine function is simply a linear function plus a constant. Again, real number. Yes. So that's what a linear function is, that's what an affine function is. Okay, what's next? We will be using a lot of vector and matrix notation. So I'll just show it, right? So one way to write this is to write down a row vector alpha 1, alpha 2, alpha 3 times a column vector x1, x2, x3 plus the constant delta. Yeah. In general, vectors in this course will be column vectors, and therefore to indicate row vectors, we'll use transpose. So one way to indicate this would be alpha is my row vector times my column vector plus delta. Yeah? So that is an abbreviated way of writing the same thing. Yeah? Okay. The reason I'm doing this is because we are going to use this notation also. I want to make sure that we are all on the same page. Because once we move a bit ahead, I will not keep translating this volume. I expect you to do it. Okay. Good. And now let's talk about linear constraints. So what you see in this program here, in this integer linear program that we have written, the first two constraints are basically a linear function equal to, less than equal to, greater than equal to some constant. This is what we will allow in linear constraints, right? So it's any f of x less than equal to beta, f of x equal to beta, and f of x greater than equal to beta, where f of x is a linear function in x, and beta is a constant. This is what we mean throughout this course by a linear constraint, right? And the only thing we are allowing, pay attention to this, is equality and inequalities that are not strict. We are not allowing strict inequalities. Why not? Why should we not allow strict inequalities? Does anybody see a problem with strict inequalities?
They don't have a proper
Why not just less than or greater than?
They don't have a proper boundary.
Right. They don't have a proper boundary. Right? For example, if I want to minimize my variable x subject to, this is my variable, the only variable, x less than 5. What's the optimum? There's no optimal solution to this, because you can get as close to 5 as you like, right? Whereas if you, maximization problem. Whereas if you put a less than equal to, now you have an optimal solution. Only 1 5. Yeah. So therefore we are not going to allow strict inequalities because we want our sets to be close sets. Okay. So that's what a linear constraint is. And now we are ready to define a linear program, which we shall abbreviate to LP. You are allowed to minimize or maximize any affine function. You're going to allow addition of a constant, because especially when you solve LPs, it will be useful to allow the addition of a constant. Doesn't really change anything. So we are allowed to minimize or maximize an affine function subject to linear constraints. That's what it is. It is any minimization or maximization problem where the objective function is any affine function subject to, I shall abbreviate to S dot E dot in many cases, linear constraints. That's what the linear program is. Right? And therefore, we have our first example of a linear program, which I will mark here in yellow. This in yellow is our first linear program. I guess our is important. Yeah, everybody agrees? Is that a linear program as per the definition? Yeah, minimizing in this case a certain linear function that is necessarily affine because it comes with a zero, subject to constraints that are all linear in the variables. Right? So therefore we have our first linear program. And what is an integer linear program? Well, it's a linear program where you insist that some non-empty subset of the variables take on integer values. Okay, so that's how we're going to define an integer linear program. Any integer, yeah, integer LP. Already go to LP. This is any LP with the additional constraint or constraints that some non-empty set of variables be integers or integral, which means the same thing. And therefore, if you include the integrality constraint, then you have our first identity. Pink is equal to pink. Blue maybe. So if I include the integrality constraint, okay, then along with the yellow stuff, what we have is our first we are insisting that all variables be integers. Questions, concerns? All good? Right, so let's look at a couple of non-examples. For example, maximize 2x1 squared plus x2 subject to, doesn't matter, x1 plus x2 less than equal to 5, x1 minus x2 less than equal to 7, x1, x2, one of them is non-negative, doesn't really matter. Right? We all agree that this is not a linear program. Yeah? We have something non-linear in there, therefore it is not a linear program. If I remove the non-linearity, I have a linear program. But now if I do this, no longer a linear program, but this is a strictly program. Yeah? So, okay. All right. Questions, concerns? Any doubts at this point? All good? Okay. So what we'll do is, there was a reason I introduced vector notation. We are going to do the same thing for this example. Right? We are going to write down the same thing using vectors and matrices. And that will also help us introduce some of the concepts that some of you may not have seen before. Okay. So let's make some space. Maybe I'll make a different graph. Others you are eligible to see. 1, 2, 3, 4 vertices, 1, 2, 3, 4, 5. So let's look at this graph here. And we call the vertices something. Maybe I'll call them V0, V1, V2, V3. And this time I will also label the edges. E0, E1, E2, E3, E4. 4 vertices and 5 edges. And objective function is not very interesting. This is straightforward. Let's just focus on the constraints. I'll write down these constraints. I will rewrite these constraints using vectors and matrices. Yeah. So let's do that. So we have. Let's focus on the. We'll give a name to things, by the way. This is called non-negativity because it is insisting that every x be non-negative. These are generally called, in the case of perfect matching, these are called degree constraints because it's like degree. In some sense, the degree of each vertex is 1. But of course, it's not really a degree because we're allowing fractions in case I drop the integral. So we'll generally call these. This one we'll call degree constraints. This is very specific to the perfect matching problem, right? And these are called non-negativity, which we will encounter in many places. So let's focus on degree constraints. Right? So how many do we have in this graph? How many degree constraints do I have? One per vertex. So I have one for each vertex. So let's look at the V01. So what is the constraint for V0 saying? It's saying that xe0 plus xe1 plus xe4 equals 1. xe0 plus xe1 and plus xe4 equals 1. This is the constraint for V0. Right? Likewise, we have for V1, V2, V3. Can you all write it down? How many vertices? 4 vertices. Yep. Here, write down all the constraints for this graph for every vertex. Yeah, it's DIM. Do it now. Not even try. Do it. Okay. Assuming most of you are making good progress, so I will start writing them myself. Yeah, all good? Alright, so you can see I've deliberately separated out the edges V0, V1, V2, V3, V4. So now can we write this as using vectors and matrices? Yeah, instead of writing all this stuff which is very lengthy, can you just introduce vectors and matrix notation for this? Okay, so what is the matrix you will get? Is that a matrix you have seen before? Yeah? What is the matrix you will get?
Incidence.
Which one? Adjacency?
Incidence.
Incidence. Which one?
Incidence.
Right, easy why, right? Adjacency is for objects of the same type, incidence is for objects of different type. Here we have rows indexed by vertices and columns indexed by the edges. So what we have is the incidence matrix. So for those of you who are not familiar, incidence matrix means you index the rows, and this example is illustrative. Index the rows by vertices, index the columns by edges, that is the standard convention, and you put a 1 whenever the vertex is an end of the corresponding edge. Otherwise, you put a 0. Right? And that matrix is called the incidence matrix of a graph. Right? Of course, you can reorder the rows and columns, but that's from an algebraic point of view, that's not very interesting. So, irrespective of the labeling of the vertices and columns, vertices and edges, you will use A of G or simply A to denote the incidence matrix of the graph. Okay? And so, if A is my incidence matrix, then how do I write this? A times X equals the all ones vector, right? And you figure out the dimensions. Okay, so therefore, let's write down the ILP again. The mean cost perfect matching ILP. The constraint that you have figured out is A times X equals 1. Because it is a vector, I will just put I'll underline it to indicate the all ones vector of the appropriate dimension. Yeah? So this is our degree constraints. These are called the degree constraints. Yes, we are done with this fellow. Now let's go to this. This is simply saying that every component of the vector is non-negative. So we will just write x greater than or equal to the all zeros vector. And the way you interpret this is that every component is greater than or equal to the corresponding component. Yeah. These are our non-negativity constraints. Let's deal with this fellow. Every component is an integer. I mean, it's kind of weird to say that the vector is an integer. This is the vector is integral. So, we want the vector x to be integral. So, these are actually called the integrality constraints. And let's deal with the objective function. What are we minimizing? C transpose X. Yeah, because every row vector is a transpose. So we are minimizing C transpose X subject to these constraints. Right? And this is the notation that we will be using most of the times. We will not be expanding out. Okay, so this was just. Questions, concerns regarding the notation? Everybody is okay with this? Yeah? Okay, so we are with this. Good. What's next? Okay. Any questions, concerns? Anything that's not clear? Okay, so let's do more interesting things now. As I said last time, you don't really need to have done a course on complexity theory to be able to do this course, but it will help you to appreciate some of the things you're learning. So I'm going to go a little bit into complexity theoretic and algorithmic discussion, because all of that is very closely related to what we're going to do in this course. So we talked about a decision optimization problem. This optimization problem that I let you know somewhere. There. We wrote down an optimization problem. Given a graph G and cost function of the edges, find the perfect matching of minimum cost. But whenever there's an optimization problem, there is also something more fundamental, maybe in some sense, called a decision problem. We're going to talk about decision problems. So, can you try to guess what the decision problem is going to sound like? What do you think should be the corresponding or a corresponding decision problem? Yeah? You?
You want to answer the question like whether it is this cost.
Okay, that would be one way of looking at it. So the first point is, so your problem, if I may rephrase it, you are given a graph and a cost function and decide whether there is a perfect matching of this particular cost. Yeah, that would be one way of posing a decision problem. Can you make it, can somebody suggest something that is in some sense closer to this one? Remember, this one is a great cost perfect matching problem.
Less than or equal to.
You can make it less than equal to. But I'm also allowing you the freedom to change the input slightly. So rather than just given a graph and a cost function, what if I allow you to take the input to be something more than that?
Given a graph and a perfect matching.
Given a graph and a cost function and a perfect matching. Okay?
Determine if it is the minimum.
Determine if that is a minimum cost perfect matching. That is another way to look at it. So there are multiple ways of going to a decision problem. The one I'm going to choose is this one. In some sense, it is closer to this one, this version. Given a graph, an edge cost function, I'll just write costs, C, edge costs, and perfect matching, M. So you're given three things. You're given the graph, you're given the cost function, and you're given a particular perfect matching in the graph. And the question is this a minimum cost perfect matching of this graph? Right? So because it is a decision problem, can we decide whether M is a minimum cost perfect matching. The fact that it is a perfect matching is clear, it's given to you. What is interesting is it a perfect matching of minimum cost? Okay. Is the question clear? Given a graph, given a cost function, and you are given a particular perfect matching of this graph, decide whether this fellow is a minimum cost perfect matching. So let's see. So given an instance, either it is a yes instance, yes, this is a perfect matching of minimum cost, or it is a no instance. No, this one is not a perfect matching of minimum cost. Yeah, is that fine here? So there are two types of instances. Either it's a yes instance or a no instance. Let's do a quick example. Let's do this graph. Why not? I've already written down the costs. We anyways know how many perfect matchings there are. So I will choose one. I don't know. I will choose the obvious perfect matching: 0, 3, 1, 4, and 2, 5. That's my yellow perfect matching. Is this a yes instance or is it no instance? I don't know. I'm not even trying, but you try to. Okay, no? No instance. Can you convince everybody that it is a no instance? How will you convince everyone?
There is another perfect
Okay, what is that?
0, 2, 1, 4 and 3.
0, 2, 1, 4 and 3, 5. 0, 2, 1, 4 and 3, 5. I'll just write it down. 0, 2, 1, 4, 3, 5. Yeah, is that the one? Okay. Oh, pink is already used. 0, 2, 1, 4 and 3, 5. Let's look at the cost of the two. The cost of the original yellow one was 7 plus 1, 8 minus 3, 5. This one is cost 5. And the cost of the pink one, 0 plus 1 plus 3 equals 4. Yeah? Sorry, can you remind me your name?
Vivek.
Vivek. Thank you, Vivek. Everybody agrees? Did Vivek convince everybody that the original yellow one was not a minimum cost perfect matching? In other words, the instance given to you was a no instance. Everybody understands what a no instance is now? And he was able to convince everybody easily that this is a no instance. Is that in general true? Can you always, for a no instance of this problem, not an arbitrary problem, this particular problem, if you know that an instance is a no instance, is it easy to convince your friend? Is there something you can show to your friend using which your friend will be like, yeah, sure, this is no instance? Yeah? You all agree? When this happens, we say that the problem is in Cohen. If you can always convince your friend that a no instance is indeed a no instance, then the problem is said to be Cohen. If you want to make this rigorous, you need to use a lot of fancy terms. Your friend can verify easily, that means polynomial time on a deterministic Turing machine. I'm not going to do that with you. Right? So, is this point clear? If no instances are easily verifiable, so what, let me make it more precise. What Vivek gave us is a certificate. The original M was the one I had given you. This was the original M. What Vivek did, Vivek told us, look at N. N proves that M is not a minimum cost perfect match. This is a certificate. This certificate exists, and if I give you the certificate, you can check that it is indeed a correct certificate. So, whenever there is an easily verifiable certificate for no instances, so if there exists an easily verifiable certificate for no instances. When this happens, we will say that the problem, the decision problem, the DP, the decision problem may cause perfect matching. Belongs to co-NP. Co-NP is a complexity class. Okay, this basically we are going into the subject of complexity. So, whenever there is an easily, I want you to pay attention to this existence. Co-NP is about the existence of certificates that are easily verifiable. Given a certificate, you can quickly check that this is actually proving that this fellow is not a minimum cost perfect match. And when that happens, we say that the problem, the decision problem, belongs to co-NP. Yeah? Co-NP. So if there is a co-NP, there should be an NP, which is more famous than co-NP. Right? So what does it mean for a decision problem to be NP? Any guesses? The same thing for yes instances, right? There is a reason I have this blank space. So, if the same thing happens for yes instances, we say that the decision problem is NP. Yeah? So now let's look at now let's think about this. Now let's look at N. Now the instance is not M. Now what I am giving you, I am going to throw away M. Now you are given this instance, the graph, the cost functions, and this particular perfect matching. Is this a yes instance or no instance? I did not check. So let me do my homework. Is this a yes instance or a no instance? Yeah? You all seem to agree that it is a yes instance. Okay? How will you convince another person? Oh, you are checking all of the perfect matchings, right? So, one way to convince is to list down all the perfect matchings for your friend. And now, if you list down all the perfect matchings, then your friend can go and calculate the cost of each and compare with the given one. And if all of them are greater than equal to, then this is indeed a perfect matching of minimum cost. But there is one problem. This was actually the answer I got in 2022 on YouTube, and I did not catch the problem. So 2 days ago, I put a comment to fix that problem. There is one problem here. So that is correct. If you give your friend all the perfect matchings, they can calculate the cost and they can check. But there is a small issue here. That is one issue. The number of perfect matchings can be many.
You have to prove that you got.
You have to prove that these are all. There could be many perfect matchings. It may not be polynomial size in the original graph size. So that's one problem. But you also have to convince your friend that these are all the perfect matchings of the graph. Which in this graph was easy because we counted the number of perfect matchings 2 days ago. Right? But in general, you need to somehow convince your friend that these are indeed all the perfect matchings. How do you do that? Yeah?
Every subset of it.
Sorry?
Every subset.
For every subset of the edges, check what gives us all the subset, check every subset and compare to the given set. Is it a perfect matching? And then check whether it is minimum cost. What is the cost compared to the given perfect matching? But that is also problematic, right? Number of subsets is 2 to the power number of edges in the graph. So that's not polynomial time. Right? So do you all see the philosophical difference between the two things in this problem? Convincing somebody that an instance is a no instance is easy. There exists a better perfect matching. That is why this one is not minimum cost by definition. Right? So you just throw that at your friend. We are not asking how you will find it. If you are wondering, oh, how do you find this n? That's not about co-NP, that goes into P. We are not talking about P right now. We are talking about NP and co-NP. NP and co-NP are not really about algorithms. They are actually about easily verifiable certificates. Yeah. So everybody sees this? Convincing that a given perfect matching is not of minimum cost is actually easy. There is a certificate. But to convince somebody that a given perfect matching is of minimum cost is philosophically much harder. It turns out that the problem is actually in NP also, but that requires theory, which is why you are here. Yes, there does exist an easily verifiable. But this existence is not trivial. This requires theory or a specific theorem. So in general, for the perfect matching, for the minimum cost perfect matching problem, the decision problem, as I have posed, it is indeed an NP. In fact, what we will do is we will see that this problem is efficiently solvable. Given any graph and given costs on the edges, we will actually see by the end of this course that this problem is actually efficiently solvable. I'm not going to focus too much on running time and all that. My focus is going to be more on the algorithms and the connection with linear programming theory. I'm not going to really focus on running time and stuff like that, which you'll probably see in other algorithmic courses in CS. But it is going to be actually popular. So what we will see is that this problem is efficiently solvable. What we call belongs to P. And if you can solve this efficiently, then it follows that you can also check whether a yes instance is a yes instance. No instance anyways is easy. So that brings us to an important point in complexity theory. So maybe I should write down explicitly that once we see this, it follows that the problem belongs to NP. So NP is the complexity class that contains those problems for which the yes instances they admit an easily verifiable certificate. ONP is for no instances. And these are sets. Problem either belongs to NP or it belongs to ONP. Maybe it belongs to neither. Those are all in a universe of decision problems. And the problems that are in P, the problems that are so-called efficiently solvable problems, they are in the intersection of NP and O. So if you take a course in complexity theory, currently who is offering COCO, you would see probably a proof of this theorem. P is a subset of NP intersection point. And a major open problem in complexity theory is that this is actually equality. Nobody knows how to do it. Let's start. This fellow here is a theorem. In other words, the conjecture is saying that this set is the empty set. The intersection minus P should be the empty set. That would be the theory flow. But we don't know this to be true. Many people believe this to be true. So I did my PhD in Waterloo, and a very famous person lives in Waterloo called Jack Edmonds. You will see Jack Edmonds multiple times in this course, not the person, but the name. He is one of the main persons behind the perfect matching problem being polynomial time. In fact, he is the person behind the fact that the min cost perfect matching problem is actually polynomial time solvable. It belongs to P. In particular, it also belongs to NP. Right? So the reason for that, at least for the P, NP I will think more. If there is anybody else who include NP, not sure. But for this problem belonging to P, it is Jack and who is responsible. So maybe I'll just write down both the decision version and optimization version. You can actually solve this problem efficiently. Given any graph and any edge costs, there is an efficient algorithm that will find a minimum cost perfect matching of this graph. And to the best of my knowledge, all such algorithms depend on linear programming duality theory and the method called the primary dual method. So that was because of Jack Edmonds. This is 1965 that Jack Edmonds proved this. And outside Jack Edmonds' house in Kitchener, which is close to Waterloo, there is a rock on which is engraved P is equal to NP intersection 1. Very interesting thing. Questions, concerns? Okay. Okay. I want to leave you all with an exercise. Yeah, I have a few minutes. I'll quickly draw this graph. So here you all have convinced yourself that n is a minimum cost perfect match. Right? But that is because you actually were able to enumerate all the perfect matches. Of course, for any small enough graph, you can do that. But maybe there is a better way to do things. Maybe, so I'm trying to kind of go to this discussion. Why does this problem belong to NP? That's where I'm taking this conversation. So I'm going to give you one graph to think about until tomorrow. Just make this graph as it is. Here in my notes. What I don't remember is the costs. So let's see. Let me put down the cost as they are here. 1, 2, minus 1, 4, 7, 3, minus 1, 3, 1, and 9. And I also give labels for the C. This is R, S, T, U, V, W. Here is a graph and your edge costs. And I'll also give you a perfect matching. Maybe somebody can try to guess. Can you try to guess what the minimum cost perfect matching is? There are not too many perfect matchings. If you pay attention, you will be able to quickly see the number of perfect matchings in this graph. Okay, let's see. Anybody else? More hands? Do something different. Get it? Yes. Good.
RW.
RW.
ST.
ST. UV. Yeah. 7 minus 1 6 plus 1 7. Somebody can do better? Done. Yeah.
RT, SW and V,
RT,
SW
SW.
and V and what is the V?
Yeah.
How much is it? 6. Can anybody do better? That's it, right? 6. Oh, I think this is correct. 6 is actually correct. RT, SW, UV. 3 plus 1, 4 plus 2, 6. Yeah, nobody is able to find better model better than this, right? Okay, good. So this is actually minimum cost perfect matching. Right, and of course the way you all convince yourselves or whoever convinced themselves, they basically listed down all the perfect matchings. There are not too many of them. And you basically compared to this and you concluded this is a minimum cost perfect matching. But maybe, like I mean, come on, that's not kind of nice, right? I mean, as we discussed earlier, how will you convince somebody in general for a given graph that these are the only perfect matchings? Also, there's another problem, which is also quite serious. In general, a graph may have exponentially many perfect matchings. So even if the number of vertices is n, the number of perfect matchings could be exponentially many in n. That's not good because we want efficient ways to do things. And exponentially is generally inefficient. Efficient generally in CS theory means polynomial time. Okay, so what we want is polynomial time within the input size. So those are problems. So maybe there is another way to convince someone that this is actually a minimum cost perfect matching in this graph. And I want to kind of give you a hint in that direction. Let me ask you a question. Supposing I take one vertex and I look at all the edges incident at that vertex and I increment or decrement the cost of all these edges uniformly. So either I add k to all the edges incident at the vertex, the cost of the edges, or I subtract k for a fixed value of k. What will happen to the perfect matching and the costs?
They all go up by this.
Yeah? You all agree? The perfect matchings, all of the perfect matchings, costs will change by the same number. Yeah? So therefore, a minimum cost perfect matching in the original instance will still be a minimum cost perfect matching in the new instance. Yeah, you all agree? And vice versa. Okay, so that's an idea. For each edge, E in partial of V for some vertex V. We will add k or subtract k from the cost. I will just say subtract k and allow k to be a real number. We shall subtract k, some real number k. Right? This is a fixed number for each edge in this. Right? Okay. Doing so results in a new instance whose minimum cost perfect matchings are the same as the original instance. You all agree? If we do this for any vertex, we will get a new instance, but the minimum cost perfect matching are exactly the same. Yeah? If I can do this at one vertex, I can also do this at another vertex. Yeah? I can do it at every vertex. So what if I do this at every vertex, but at every vertex I can choose a different k? You can think of some kind of labeling of the vertices. For every vertex I will give a label. That is my k of that vertex, or L if you like label. Right? And I will just perturb by that value. Right? I'll just subtract that value. That value is something around here. Can this idea lead us anywhere? I mean, at this point, it's useless, right? It doesn't really. So, what would be nice is somehow by doing this, I can reach a certain configuration. Then it would be very nice. Does anybody see?
So the minimum perfect match should have 0 from and others should be positive values.
Or non-negative.
Non-negative.
Is that okay? Yeah. Right. Jaiprakash. So what Jaiprakash is suggesting is that if we can find labels, we don't know whether they exist in general, but if we can somehow find labels for each vertex, you subtract that label from all the edges incidents at that vertex. And after doing this, if all the costs of the edges in the new instance, they are all non-negative, and this fellow, M, this yellow perfect matching, if its cost is 0, if the cost of the yellow perfect matching is 0, and every edge, the cost is non-negative, then it proves that this is a minimum cost perfect matching. You agree? Now it would be magical if such labels existed, but maybe they do. Maybe not for all graphs, maybe for some graphs. And maybe for all graphs we need something more sophisticated. So that is actually what's going to happen. Turns out, for this particular graph, you can actually find labels that will do this. And that's your TIY until tomorrow. So, TIY. I don't like K, I'm going to make it L. Labels. Find labels. L. You may think of L as a function from the vertices to the real numbers. Yeah? Such that the new instance, you do this at every vertex according to the labels, such that the new instance or the final instance, has two properties. Satisfies the final instance, satisfies the cost of each edge is non-negative. I'm going to call it C prime. This is the final cost after doing this. C prime of each edge is non-negative. And the cost of the given yellow matching, this fellow, C prime of n, is 0. If you are able to find such labels, then you don't need to enumerate all the perfect matchings for your friend. You just tell them, here is a set of labels, and now I have therefore proved to you that this is a minimum cost perfect matching. Right?
Here, arbitrary cost arbitrary.
For each vertex by any arbitrary real number. Yeah? You agree that it will not change the set of minimum cost perfect matchings. Think of one vertex at a time. If you do it at one vertex, it doesn't change. Do it at the next vertex, doesn't change. Do it at every vertex. Right? But different vertices can have different labels. So anyways, yeah, so work it out, and if it works out, it may seem a bit magical, and we will see these things going further in the course. In fact, this is going to be related to one of your assignment problems, I want to make a quick comment about the assignments. I am very unhappy with the fact that the drop deadline is 14th of August. In earlier semesters, the drop deadline used to be much later, September, October or something. And what I would do is, therefore, by the time the drop deadline arrives, you would have had at least one assignment submitted and gotten the marks and feedback and everything. And you will be able to make an informed decision what to do. Unfortunately, the drop deadline is 14th August. So, yeah, there is not much I can do. I will release the assignment this week itself. And I can make it due before 14th August. But that's going to be a bit tight for all of you. So if you want, I can make it, or I can make it 10 days, which is my typical policy. Right? So I have mixed feelings about the thing. Anyways, so think about it, and my plan is to give you 10 days. But if there's a demand from all of you, make it 14th August, I'll make it 14th August. Then you make a decision whether you want to credit, audit, or not. Yeah? Okay. Any other questions, concerns? If not, I shall see you tomorrow at 3:30. Thank you.